Welcome back. So we talked about adaptive SGD, which is a more principled way of tuning the learning rate in terms of the estimation of the variance, which was one of the parameters we may need to know to get the best learning rate. We can estimate it on the fly by leveraging the observation we have gathered while training our model. And the observations are basically the gradients, or the stochastic gradients rather. Okay, so and this was basically the learning rate we ended up using. In practice, we actually use slightly different ideas. Okay, and this method is I would say a simple version of famous methods, very popular methods such as AdaGrad, AdaDelta, RMSProp, and notably the Adam optimizer that we're going to cover in future lectures. Okay. So one essential idea that many of these algorithms use is that instead of a simple averaging, like we are here, or a simple sum, like we have here, they use a weighted averaging or a weighted sum, such that we put more emphasis on recent observation. Okay, so if I've trained my model for 100 epochs, right, the variance near the 100 epoch might be completely different than the variance I was experiencing in the early phase. So why should I put the same weights on observations I gathered in the early phase of training and the observation that I'm gathering now, or I've gathered very recently? So that's the main idea. We want to put more emphasis on more recent observations. Okay. To do that, we use this weighted averaging. So I just introduced these weights. Okay, with some beta tilde, which is a parameter between 0 and 1. Okay. So as we can see here, if tau is equal to 1, meaning that I'm considering a very old observation, beta, which is something between 0 and 1, has a very large power. So therefore, it is a very small weight. Okay, so I'm discounting the contribution of let's say, the early observations. On the other hand, when tau is near t, the power of beta tilde is small, let's say it's 1. So therefore, I'm using a much larger weights for the more recent observations. Okay. We can also talk about this in terms of moving averages. Okay. So another way to basically write down the same thing. Okay. And that's where the name exponential moving average, or EMA, comes into the picture. Okay. So, in particular, let's imagine that we have this learning rate. Okay, so it's just some constant c, some constant for numerical stability, kappa square, and then the more important thing is t times st. Okay, so st, you should think of it as basically the variance at time t, or t times st is basically the accumulated variance so far. Okay, previously we basically had a simple moving average, meaning that the accumulated variance or the variance at time s is basically depends on the variance at time t minus 1 and the current observation using this formula. Okay, so this is basically talking about, again, a simple average, but in terms of moving average. Okay, so it's exactly identical to this guy. It turns out that what I have here is roughly also equivalent to what I'm writing here, which we call exponential moving average. The variance at time t is some beta times the previous variance plus 1 minus beta times the current observation. It's basically a weighted, like a convex combination of st and st minus 1 and gt. Okay. Now, here you can also see the issue, right, with using a potential issue with using a weighted simple moving average. Okay, and the idea is that imagine t is large, right? So I've trained my model for like 100 epochs. Okay, so what I'm doing here then, by simple average, I'm putting a lot of emphasis on the prior observations, and I'm basically not putting enough emphasis on my current observation. So I'm diminishing the contribution of the new observation, okay, as t increases. On the other hand, if I use a fixed beta that doesn't, let's say, change with time, okay, I will make sure that the contribution of the new observations are not diminished with time, okay? So in particular, I'm replacing 1 minus eta t with beta, okay? But nonetheless, this gives you, because 1 over t is, let's say, a small number, this gives you an idea of what kind of beta you should use in practice, okay? So again, 1 over t is a small, so 1 minus 1 over t is something that is very, very close to 1, okay? So therefore, in practice, what we do is that we actually set beta to be very close to 1 as well. For instance, we may use beta to be 0.99, which I believe is the default value that's used in the Adam optimizer we'll be talking about in future lectures, okay? All right, so therefore, I would say we end up using exponential moving average as opposed to a simple average when employing adaptive SGD in practice. Doing so, on the other hand, has some issue, okay? So recall, for adaptive SGD, we talked about two crucial properties, causality and also the non-increasing property. Both of them were essential to ensure, to make sure that we actually can establish convergence guarantees, okay? With exponential moving average, we're not going to lose the causality, okay? We are still relying on the current and previous observations to estimate the variance, but we may actually lose the non-increasing property of eta, okay? So in particular, this bad case could happen, meaning that, so if I want the non-increasing property, I want to make sure that eta t is at most eta t minus 1. So you do the comparison of the denominators, and then you'll arrive at this condition, okay? So this is for the adaptive SGD case, and this always holds. That's why we actually have the non-increasing property, because again, we are accumulating positive terms with the same weights, so we're not going to lose this property. On the other hand, this condition is not, as I said, it's going to happen for simple averaging, but it's not necessarily going to happen for exponential moving average. It's not going to happen if this event holds, if the norm of the gradient square is less than this quantity, okay? And in fact, it is likely, this is likely to occur when t is large or when beta is small, okay? Or both. So therefore, this gives you an idea of why, again, we want to use a beta which is very, very large, and by that I mean a beta which is, so by small I mean a beta which is near 0, and by large I mean a beta which is near 1. So you want to make sure that beta is near 1 to reduce the chance of this bad event happening, and therefore we lose the non-increasing property, okay? But nonetheless, even if we use a large beta, this could happen if t is large, okay? So what will happen? Why is it important not to lose the non-increasing property? Because if we lose it, the learning rates start to go up, okay? Start to go up, and not only we're going to basically not necessarily have a theoretical analysis anymore, but also this could lead to training instability, okay? So remember, when t is large, you ideally want to be very refined in your search. But as t goes up and we are losing this property, step size could become large. So we're gonna lose this refinement in our search. And even worse, it may actually lead to some divergence issues. And this is indeed something that we have seen in the literature happening for some of these methods that use exponential moving average. So in particular, there are cases that you can show these methods suffer from divergence issues, even for very, very simple functions, even for some basic convex optimization problems. So why do they work for deep learning problems? That's a sort of somewhat a mystery. But I would say the idea is that it is very unlikely for this to happen if you are using a very large beta. Okay, so this again gives us an idea of how to fix this potential issue. Okay, one fix is to make sure beta is near 1 and do not overtrain. Okay, so don't use a very large number of epochs. Okay, another fix is to implement safeguarding mechanisms. So the idea is that we want to make sure that we always have this non-increasing property. Okay, and the safeguarding mechanism is actually very simple. You just make sure that the denominators don't decrease over time as a result of using the exponential moving average. So in particular, we basically want to ensure that our new denominator is the maximum between these two. Okay, so it's a very simple derivation, so I don't want to bore you with that. Okay, it's just that it's just going to ensure that we again retain this non-increasing property. Okay, and this idea leads to a very famous algorithm which is called AMS grad, where you can basically just modify any of these methods using exponential moving average, such as RMS prop and Adam, to make sure you have this nice property and therefore you don't suffer from divergence issues. All right, so we talked about adaptivity with respect to the variance. There is another notion that we want to be adaptive with respect to, and that's the notion of curvature. So the curvature of the landscape. Remember, we are solving optimization problems that are multidimensional, right? So if I have 100 million parameters, I'm basically optimizing a function, or my landscape is in 100 million dimension space. Okay. So what we have observed is that naturally, okay, different parameters exhibit gradients with widely varying magnitudes. For instance, maybe parameters in layer 1 evolve faster than parameters in layer L, maybe the last layer, because they have a larger magnitude, okay, or vice versa. It's just that again we are in again like a multi-dimension, so some sort of directions may be more steep than the other directions. So therefore, the gradient or the directional derivative along that direction could be larger than the flatter directions. So therefore, we may update some parameters faster than the other ones, okay, by using the same learning rate. Okay. So this is something that it is desirable to sort of be adaptive to. So we want to be adaptive with respect to curvature. For curvatures that directions that are steep, we want to make sure that we are careful and we are not using a large step size. And for the directions that are flat, we want to basically make sure that our learning rate is large enough such that we make meaningful progress. Okay. So this gives this leads to the idea of per coordinate learning rate. Okay, so where you use a specific learning rate for each parameter or a group of parameters. Okay, so for instance, for parameters, the weight matrices of layer 1, you use a learning rate. For weight matrix of layer 2, you use a different learning rate, and things of that nature. Okay. So therefore, our method is going to be something like this. We're going to update each coordinate separately. The update, again, has our usual form. We go from one parameter to the next by using the negative direction of the stochastic gradient times a learning rate. But I do so for each coordinate separately. So that's why we have, for instance, WI. Okay, so that means the IS coordinate of my model. And the learning rate takes the form of our adaptive learning rate we talked about before, except that again we use this idea for each coordinate separately, such that we are basically estimating the variance of each coordinate separately. Okay, so this is basically the accumulated variance for coordinate I. But nonetheless, it is almost identical to what we had before. Again, the motivation is similar to normalization methods. So we are normalizing the directions separately to make sure that we are not suffering from divergence issues. So there is a nice intimate connection between, again, pair coordinate, adaptive step sizes, and normalization techniques such as batch normalization and layer normalization. Now, in terms of the analysis, it's actually, I would say, somewhat simple, okay? So, and it's intuitive. So I have a d-dimensional problem. It's as if I'm solving d one-dimensional problems. So the idea is that we can basically leverage the properties of the Euclidean space. For instance, this was one of the terms we had to deal with when analyzing, let's say, SGD for convex functions. Okay, so we were interested in this inner product. Using the definition of the inner product, this is basically sum over the dimensions of these smaller products. Okay, so using ideas like this, we can basically analyze one-dimensional problems using our previous analysis. Okay, and then sum them up. So sum all the errors up. Okay. And then we'll be able to get like a nice one on the accumulated suboptimality gap if we are talking about a convex function, or let's say the accumulated gradient norm if we are talking about general non-convex functions. Okay. All right. So that's about it. Then in this lecture we talked about principal approaches to tune the learning rate, if you will. In particular, we talked about two different notions of adaptivity. Adaptivity with respect to the variance, and also adaptivity with respect to the curvature. Okay, so meaning in flatter region, we want to use potentially larger learning rates than in a steeper region. Also, we talked about this exponential moving average, which is an integral part of advanced training methods that we're going to start talking about in our next module. I'll see you there.